Well, thanks a lot, first for the nice introduction and also to the organizers for including our paper in this very nice program. Yeah, this is joint work with Phil and Max, and the usual disclaimer applies. So this talk is really about interpretability and interpretation. And typically, when we think about interpretation, especially also in the context of machine learning forecasts, we think about variable contributions. So which variable is driving the prediction, and how we solve this typically is, we have a certain model, we have a conditional mean function f, and then we will, we interpret it via its partial derivative. So in a linear case, what would you do? You would take the partial derivative with respect to a certain regressor, and you would get the beta. But even in linear regressions, this task can quickly get challenging. And the problem that we have is the number of variables that we want to include. And in macroeconomic forecasting, typically, we want to include a rather large set of variables. So we want to really have this kind of snapshot of the economy with a lot of macro indicators, financial variables, and so on. So if you think about such a system, it's like, 150 cross-correlated variables. I mean, this partial derivative, it gets basically meaningless in such a system. And then when we move beyond linearity and we use nonlinear models, this problem gets even worse, because then this function is super complex. You cannot even take the partial derivative that easily, and you even usually expand the feature space, so you take lags, you take moving averages, etc. So this problem gets even worse. There are solutions in the literature, and they all, or most of them, focus on reinstating sparsity in the covariate space, right? So what you could do is you could use regularization, so for example, shrinkage, or other forms of regularization. You could even handpick variables. But what if your problem is actually dense? Then I guess you wouldn't really want to do it. The dense solution to this would be factor models. So you could move into this kind of latent space and extract the latent factor. But then in terms of interpretability and also communication, latent factors are also kind of tricky to communicate often. So for us, the key takeaway was, okay, we need some kind of sparsity for interpretability, and preferably we like linearity, because that's usually for us easier to think in linear terms. And so we looked at this problem again, and especially in macroeconomic forecasting, you have two dimensions. Now you have the variable space, but you also have the time series dimension. And so we thought, why not interpret the model via its time series dimension? And the advantage is that it's already short, so you already have kind of a sparsity there. And so I also stated this in the second point. Now, so when you look at the regressors, we call it P here, this is often even larger than the number of observations that you have n in your model. And usually we don't like it because it comes with a lot of statistical cost. But here we show that maybe we can just use it and interpret the models via this kind of more manageable number of n. And then also the very nice thing is that when you look at machine learning models and the ones that we are typically using, they are highly nonlinear in X, so that's what we like. Now we want to have this nonlinearity there, but they remain linear in Y. And so this is also a nice insight here that we can leverage. And how do we do this? We use duality. Okay, so what does duality tell us? It tells us that you can have an out-of-sample prediction. This is y hat here on this slide. And you can actually decompose it in two ways. So we are usually, we look at the first one, so the left-hand side, the primal solution. Now, I have here the linear case, but still, the point is that what you usually do is you estimate your model, you get a beta hat here. And then you apply your out-of-sample regressors and you get your prediction. But this beta is in dimension p, and I already said in macro forecasting this can be huge. And so what you would do, you look at, 1,000 bars here. And even worse, if this is a dense problem, then you would look at the 1,000 bars that are all kind of small but significant in a way. And so it's tricky to interpret this model via this dimension then sometimes. So there is a second solution, and this is the dual solution. And it tells you that the very same out-of-sample prediction, so this is important, this y hat is really the very same out-of-sample prediction, can also be decomposed into the contributions of your target observations. And what you do is you kind of back out these weights that we call W here, and then your out-of-sample prediction is basically a weighted average of your target observations in the sample. And the nice thing is this W is of dimension n, and so this is now the time series dimension. And in the charts here, you see kind of a preview of what we will be looking at later in the empirical section. And so in the panel below, this is really basically the W, so we call it forecast weights, because it kind of tells you the similarity the model finds of current conditions with the past in your training data. So this is the W, and then you can also look at forecast contributions, meaning you can multiply these weights with your target observations and then get to the final prediction that we are interested in. And yeah, why we think this is interesting is because, you know, these weights and these contributions, they can tell us something about the model, what does the model find, and it can help us to interpret the model and the results. So for example, here, I mean, we're looking at US inflation. I will get back to this later, but you look at two predictions, red and green, and you can see, okay, for the red one, the model finds similarities to past recessions. In the green one, it finds, for example, similarities to the oil crisis, and we believe this can be interesting on its own. Yeah, so I guess the key takeaway, because I think this slide is really important for the paper and also for the talk, is that we still think it's important to look at variable importance, of course. So we view this more as a complementary tool to also look at this time series dimension and kind of ask the model, okay, where did you learn from, which periods were important for this certain prediction that you will give us. Okay, so the contribution of this paper is we propose this complementary tool, as I mentioned, and we show how to obtain these Ws for a set of different models. So we have linear models, nonlinear models, kernel-rich regression neural networks, tree-based models. And the nice thing is that it requires little to no additional computations beyond what you already did. So you can estimate your model, and then you can kind of back out these weights, and I will show you how this works. And then we also show how to interpret these weights, okay? And for us, we view them as kind of portfolio weights, quantifying this pairwise observation proximity as perceived by the machine learning model between now, or kind of at the time you make the prediction, and your training data. And then we'll have empirical applications, and I will show you post-pandemic inflation and maybe GDP if we have some time. Okay, so how do we get to these Ws? I would like to start with the linear model because that's kind of the backbone also for the nonlinear cases. So the linear model that I want to show you is the rich regression, because in the rich regression literature, this concept of duality is actually well known. So you can Google it or ask ChatGPT, no? And you will get this. So this is not something we came up with, but we just want to use it for interpretability. That's the point. So in a rich regression, it's a regularized linear regression. So you minimize the squared error loss function with a regularization term. That's what the lambda, the penalty term here, the lambda gives you here. And then the primal solution, that's what we basically all know. I mean, if you take out this regularization term, it's basically OLS. And what the primal solution does, it focuses on covariance. Now it's this covariance-based solution with the x prime x. There is a dual solution which focuses on inner products. And that's where this kind of proximity-based interpretability comes from, because, you know, it's really numerically equivalent, but the thing is that it's kind of answering a different question. So on the one hand, you focus on covariances. In the other solution, you focus on inner products, and that's where this proximity kind of view comes from. And so we can apply this to our prediction problem, and so we will have a covariance-based prediction. That's what we know. And then in our case, we are more focused on the proximity-based prediction, and then we define this W in a way so that it's kind of this linear combination of your Ys, your target observations. Okay, so what is this W? I mean, this is important for interpretation, so it's important for us. You can kind of disentangle this W into two parts. On the one hand, you have these plane proximities, so this is kind of easy to interpret. Now it's this inner product, this gives you this kind of distance. But then you also have this proximity denominator, which is a bit more tricky to understand. So how we think about this is if you go back to OLS, so this x prime x, x prime y, you can actually think about this ideal world where your x's are uncorrelated. And if your x is uncorrelated, what happens is that this x prime x, it's the identity matrix, and then the dual and the primal solution are exactly the same. Okay, so we think this is kind of a nice insight to also understand, you know, this concept of duality and make it a bit more approachable. But we are not living in this ideal world, right? So our x's are not uncorrelated, but you can still achieve this kind of, but in a transformed space. So what we do is we factorize the covariance matrix, and when you do this, you get orthogonal features again, right? And then this kind of equivalence holds again, but it's in a different space, so to say. That's how I like to think about it. And so the role of the proximity denominator is really to make sure that this equivalence holds between primal and dual, but in this factorized space. Okay, in case I lost some of you, let me give you some intuition about the W itself, because this, I think, is more the important part of this talk here. So let's say we have one training observation. So you observe inflation in 2010, and so this would be the Y, for example. And you observe GDP and unemployment, and yeah, this kind of snapshot of the economy in 2010. It would be the X1. And then you observe your X2, which would be GDP unemployment, let's say in February 2026, and you want to predict inflation in March. What happens now with this W is that if this X in February 2026, so GDP, unemployment, and so on, is exactly the same than what you observed in 2001, then this W will be 1. So this would tell you there is this high proximity, no? Because for the model, it kind of looks like the same thing. And that's why you would get Y2 is Y1 in this very simple case. No? And then we do this for this whole kind of target sample, and that's how this W evolves. But the important thing is that, yeah, we can really interpret this W as being this proximity measure kind of to the past. Okay, so I was talking a lot about the linear case, but I think it's important because what is coming now is really based on this, basically. So the first nonlinear model that I want to show you is kernel-ridge regression. In kernel-ridge regression, or you can also think of Gaussian processes, obtaining this W is actually very straightforward because these models, they are already saved in the dual space. So what happens in kernel-ridge, we introduce new nonlinearities by expanding the feature space. By doing so, this problem can get infinite. So what we do is we solve it in the dual space. So we introduce kernels, and then we solve it that way. And what this means for us is just that this introduces a different notion of distance. So instead of using the Euclidean distance, like this linear version, we can now use, I don't know, a Gaussian kernel for the Gaussian distance, a Laplacian kernel, whatever. And how you obtain the W is actually the same as before in the ridge regression case, but instead of using the plane x's, you now use the kernels as well. Okay, then the other model that I wanted to show you is neural networks, because yeah, we are in this AI conference, and when we talk about AI, we often think about deep learning, right? So I also want to show you neural networks. What I show you here is actually a quite simple architecture, but this extends to also more complex versions of neural networks. So I just thought about Cronus, actually, during the talk before. And I have to admit, I mean, Cronus 1, yeah, maybe it would work. Cronus 2, rather tricky. So I guess we would need to talk about this in more details. Because in Cronus 2, the problem is that the loss function is a quantile loss function now, and a quantile loss function is not linear in Y. And what is really important for us is that it's linear in Y for this to work. But we can see, maybe we can extend this, but I'm not here to brainstorm, so let me try to explain what we did so far. So in a neural network, what you do is you obtain your prediction recursively. So you move from the x to your y over layers, basically, no? And in our case, we view them as generated features. So you start with your input data x, and then you feed it into this neural network, meaning you estimate coefficients, which they call weights in this literature. You estimate a bias term, which we would call the constant, and then you apply this nonlinear function, which is called the activation function. And so you do this for every layer, and then what you get in the end are kind of generated features. And so for us, for this thing to work, is that this last layer, the output layer, is linear. It sounds a bit restrictive, but usually it's not, because usually when you design a neural network, your output layer would be a linear one. So usually this works, but just important to mention that the output layer needs to be linear. And if this is the case, then we can again do what we did for rich regression. We can again use this kind of inner products to solve the model and to get to the prediction. And instead of using the x's, we now use these generated features. Also important, this is not an identity, this is a good approximation, because in a neural network you use regularization, you use dropout, and so on. So this is not an identity, but it is a good approximation as long as your neural network optimized, and as long as it's doing a good job in the estimation. And if this is not the case, I mean, to be honest, you should not be using the prediction anyway. So if your neural network is optimizing, if this is a good prediction, then also our method would work to get to these W's here. Okay, final class of models is tree-based models. And here I show you random forest, and we also have boosting in the paper. The nice thing is that in this strand of literature, this is already shown that a random forest can be viewed as a linear combination of the y's. And so actually, we just take what is already there, and we kind of see our contribution more in taking these W's and really like plotting them and look at them and interpreting the model via these W's here. So there are papers in the literature also for boosting that show you how to extract these W's. So I will move on. Exactly. So we visualize two things. That's what I actually already showed you in this first slide that I showed you. So we have the forecast weights, the W's themselves, and we can just plot them as a time series. These are kind of our proximity scores. And we have forecast contributions, and this is the weights times the W. You take the cumulative sum, and if you do that, you end up at your final prediction. So you can really see how this prediction evolves in the training sample. Okay, so in our empirical application, we use quarterly data from FredQD. We have 240 macroeconomic exponential variables that are in there. We use lags, moving averages, and so on. And just to mention again, what you end up is like almost 2,000 regressors in your model. But you only have 250 observations here. So we started in the 60s and end in 2024. So yeah, again, now you see that this is really, you have this large set of regressors, but this kind of small set of observations here. We do direct forecasting for inflation and GDP growth, and this is, I show you examples from post-COVID. And we have this inclusive set of models, a linear model, kernel-rich, what I showed you, tree-based and deep learning models. Okay, and now we can look at these charts again that I already showed you. Now on the left-hand side, you have these forecast contributions. And on the right-hand side, you have the weights, these W's that I talked about a lot now. You have in black actual inflation. And you always see which models I show you in this kind of title. So LGB is boosting, and then is the neural network. So for example, we focus here on 3 specific predictions. Now, because you get these weights for every prediction that you do, that's important. So we focus on the quarter right after COVID, so 2020 Q3. We focus on the onset of the surge, 2020 Q1, and the peak of the surge in 2020 Q2. And then we can look at these weights and kind of answer these questions: where did this model kind of learn from, or which periods this model kind of learns from, and where are these kind of similarities? Where does this model see these similarities? So, for example, this first prediction right after COVID, we do see similarities to past recessions. This is what you see in blue. And then we also see that the neural network, for example, it finds these similarities as well, but it finds this mainly with the great financial crisis, which gives you this really low kind of deflation prediction, which we know, and also probably as a practitioner back then, you kind of knew that this is a bit too low. And so you could have a look at these weights and then say, okay, maybe we are a bit overstating the importance of the great financial crisis, just as an example. No? Then you can look at the onset of the surge, and here, I mean, what the models give you is basically the unconditional mean. So it looks like, they're not really finding much similarities, or not like with specific periods in the past. So what it gives you is more like the unconditional mean. And then for the peak of the surge, we see that especially the boosting model, it finds the similarities to the oil crisis in the 70s and 80s. So this was also this high inflation period where it seems that especially the boosting model finds this kind of similarities and learns from. Exactly. So yeah, and then we also thought, I mean, as a practitioner, you could really use this tool also to kind of explain surprising predictions in a way. So in the upper panel, you see this prediction from the boosting model actually during COVID, which is very precise, and it's a bit like surprising that the model gets it this precisely. No? And so we look at the weights and we see that the weights are really sparse. No? So in this case, it really finds the similarity to the great financial crisis, which gives you this low inflation prediction. And the neural network, on the other hand, for example, in 2020 Q2, where we already kind of knew that we are in the surge, or we already saw inflation going up, and now we see again this kind of low prediction, which is a bit surprising as well. So you could ask, okay, is this really what is happening? And you could look at the weights, and at the one hand, we see it's rather volatile, but we also see that it puts a lot of weight on this low inflation period here between, so in the great moderation and so on. So we would probably say, okay, we don't really think that this is the prediction we want to fully trust, I guess. Okay, yeah, and then I think I still have time. So we can also look at GDP growth. I mean, we mainly worked on this paper in 2024, I have to admit. That's why we called it recent predictions. I mean, now we know what happened in 2024. But back then, the discussion was around, are we facing a recession in the US? And so we did these predictions, again, with neural network, and also here we used kernel regression. And then we did a 1, 2, and 4 steps ahead prediction in this case. And we saw that, especially the neural network, it did find some similarities to past recessions. And what is actually remarking here is that it did so for the longer horizon, because typically the longer the horizon, the less signal we have. No, but in this case, the neural network was really seeing this downward path. So we found this interesting in this case, especially because it's for the longer horizon. Kernel regression is a bit, less certain about it. No, so it's more. I mean, it's also a bit like a downside prediction, but yeah, not so much. No, it's also more the unconditional mean that we get from the second model here. Okay, I'm a bit faster but I think it's good. Now we have more time for the discussion. So my concluding words would be that, yeah, so we really view this as a complementary tool. We still think it's important to also understand which variables are driving the prediction, but we also think that it's nice to look at predictions in this way, because also it's a very intuitive way of doing things. Now, so when we talk, or also in the media, it's often the discussion around, okay, is this actually similar to what we already saw? Is this similar to the dot-com bubble? Or is this the Iran war? Is this similar to what we saw during the invasion of Ukraine and so on? No? So I think this is kind of a tool to visualize a bit things in this direction. What would the model tell us? There are a lot of avenues for future work, we think. So first of all, it would be nice to have inference also for these Ws. We did not work on it, so I can actually not really tell you more on that, but we thought it would be nice to think more about these Ws. And then, yeah, you could also think about different things to do with these Ws as well. Now you can also use it, shrinkage or regularize the Ws themselves even, and so on. Or also use it as a tool to put some kind of judgment into models. Maybe now if we see that there is a high weight that we don't really think, we as practitioners that it's true, we could use it maybe as a tool for judgment and so on. So I think, there are many avenues for future work, and thanks for the attention. I'm looking forward to the discussion.
Thank you, Karin. The discussant is Galina, please. The floor is yours, and you have 10 minutes, as everybody.
Yeah, thanks so much. And thank you, first of all, to the organizers for the very kind invitation to this conference, and to Karin for the great presentation. I was very happy to read and discuss this paper, since a lot of my work in the sphere of forecasting and machine learning precisely looks into making machine learning more interpretable, and actually not only looking at forecasts, but also telling a narrative around what machine learning can do, and which nonlinearities it detects. So this is very close to my heart. And what the paper does, and Karin presented it very well, so I can keep this short, but it discusses an alternative and intuitive way to interpret predictions, rather than in the correlation space that is based on the features and the contributions from specific features. Here we look at proximity to past observations that are part of the training samples, so to past historical episodes. And this gives us this data portfolio weight, so the authors choose kind of this financial portfolio wording that reflect ultimately the proximity between current and past economic conditions. And this term Kj will give us the similarity between the new observation J that we're aiming to forecast and each training point in the past. And then Karin made this very clear in her presentation. They say that this dual interpretation is readily available for linear models such as the ridge, but then they show for a range of machine learning models that this is also possible, and as Karin says, it does require some additional structure in some cases, like for neural networks, the linear final layer. They also make it quite clear that this is particularly useful for macro applications, since we have this historical dimension that is usually much sparser, so shorter and easier to trace than the cross-section, and therefore they have this range of empirical applications. The ones in the paper actually looked for unemployment and GDP growth on 2008, but now you have even more recent ones. Inflations, also for classification problems, so predicting recessions were included, and they then run forecasts for specific quarters in each of these episodes using a range of these models. Now, what I like about the paper is I think that this historical nearest neighbor interpretation is really useful to policy, and I think this is also made very clearly and intuitively in the paper. And I really see also in my kind of policy work at the Bank of England that this is very closely to how policymakers think. So we have usually a lot of outputs in terms of forecasts, contributions, impulse responses, and then often the first question is, so how should I think about it? Are we now close to the 70s or to the global financial crisis and so on? And I think especially in the current environment, maybe I was actually more convinced about the paper now than when I first saw it 2 years ago, because in the current environment, we're really facing this with the ongoing oil price shocks. The big question is really, are we now close to the 70s? Are we close to the 2022 episode being repeated? Or can we find past episodes where we had this constellation of oil price shocks, but also more slack in the economy that might be different to 2022? So I feel like having this dual view is something that I would find also useful to present some of my results with. But as you made clear in your talk, but maybe it came out a bit less clear in the paper, I would also see it more as complement to existing tools, also to Shapley values that we have available in machine learning, or as well to some additional structure that we add to the model. But generally, it is good if we can broaden our set of interpretability tools that we can rely upon depending on the question at hand. Now, I have a set of questions here that are more in terms of conceptual, and then I have some on the empirical application and the outputs you're showing. On the conceptual side, I was really wondering, so does this approach really have a distinct advantage for more complex and opaque models, which I think is something that you base your paper on, that you really have either nonlinear machine learning models or factor models. Of course, your empirical setup is already a biggish data kind of question. But ultimately, I would think that this is also useful even for a very small linear model, like a free variables prediction, like Philippe's curve type regression. So, and maybe the interesting added value here is that we have a metric that is comparable and that can give us similar metrics independent of whether we have a small model or a large and complex model. And then for the opaque models, I'm not sure, do we really solve the interpretability question here, or do we kind of overcome it or like dodge it a little bit, which is good if we can't solve it, but maybe we still want to complement it with a bit more of understanding of what the models do and why they then load on give weights to certain episodes. So then this weighted view can really maybe help us understand the model, but that would, I think, need some combination with Shapley values or with an added structure. And you have Philippe's HNN model in there, so maybe that can be an avenue. And ultimately, yeah, there's a broader applicability question with, can we have this also for VARs? I think you have another paper on on local projections, so that is something I would find of interest. And then the range of outputs, you discussed two here, the weights and the contributions, but you actually list a wider range in the paper. This is a similar chart of what you've discussed, and there are quite a few of these charts in the version of the paper that I've seen. I think some of them are really intuitive, like the one I think you focused on here for inflation. You really see for the first two models, they're very clearly distributed weights. But then for this third model, it's already a bit less clear. And I must say I found the cumulative ones far less intuitive to read, or at least I maybe didn't need more than one of these charts. But what I actually found quite an interesting chart, and which only popped up once, and for a subsample, were these contributions. So this already also is the weight times the prediction, and in a moving average form. So I found this showed also how, so for instance, this model has a clear weight on the 70s, 80s, but it also showed a much clearer picture now for the HNN, that basically some of the volatility we've seen for the weights comes maybe for this, that the model reads the opposite directional information. So it says that 2020 here was very different to the 70s. And you also have this short position as one metric that shows you whether the model exploits asymmetry. So maybe that is something worth exploring further, because this is an advantage that these nonlinear models can have, that they will not necessarily read information symmetrically. And another interesting chart I thought was this, where you just kind of group sub-periods of your training data and show the historical importance. You do this also for your selected predictions. Though what I would found even more interesting, if you have a range of out-of-sample predictions, if you have an entire out-of-sample period, and then you could show this for subparts of the out-of-sample period. So this brings me a bit to my final point on how the empirical design is set up. I felt it was a little bit fragmented, so you have many applications for 3 different variables of interest, various episodes, and in each of those you usually look at specific quarters, so a bit more like case studies, which I think serves well to make that point in crucial moments of time. But it is maybe a bit less convincing in terms of, is this something that holds more generally? And also, it is a bit difficult to square. We see that some models interpret it this way, other models interpret it that way, but is this reflected in better forecast performance? This was a bit less clear for me, and I think here you can actually add interpretation apart from the visualization by linking those two. So my suggestion would be to maybe pick only one application as the main one. I think in your talk you focused a lot on inflation. I think that makes quite a lot of sense. It remains timely. You could maybe move the other ones more in the appendix. But then maybe you could do a systematic forecast evaluation first over a longer out-of-sample period, say starting from 2000 or a bit later. Of course, the question is a bit how computationally intensive this will become. But then you could have an entire out-of-sample period, which you could even split further and say, were there any shifts that a model that during the low inflation forecasts was weighing a lot on standard, on quiet episodes, then moved towards reading a lot from the 70s in the high inflation episode. And there, I would expect that maybe nonlinear models did this to a greater extent, and that could be actually a justification that this tool is helpful for nonlinear models. And then I think the targeted case studies are really interesting in addition to that. So that's from my side, but overall a really interesting paper, and looking forward to hearing more about it.
Thank you. Karin, if you want to reply to some of the points raised in the discussion.
Yeah, thanks a lot. No, thanks a lot for the great discussion. Yeah, I think that you're fully right. I mean, now that we submitted the paper, we really had to narrow the scope also. I mean, there was a lot of stuff in there, a lot of applications. But first, we wanted to be broad, now to be also convincing in a way that this can be useful. I mean, what I think, because you brought it up now also with the performance, it's true we use off-the-shelf models. So none of these models were really kind of targeted for a specific application or kind of tuned or anything. So we tried to use off-the-shelf models and then see, you know, okay, the performance should be okay, but we didn't really invest much into making the performance like exceptionally good or better than others. For us, it was really more to get the interpretability point. But I agree that it would be nice also to see even if this is related. Now, if the performance is better, if, for example, the weights are rather sparse or rather dense or things like that. So there I agree. And also, because you mentioned why do certain periods matter, I think it's a very important point. What we thought about, but we haven't really worked on this, is how we could combine the weights with actually, for example, Shapley values, or you kind of to have both views. No? And it would be, for example, nice to have like implied weights for each regressor or something like that. But it's I think it's a new paper, to be honest, because here we try to show, you know, what you can do and how you can extract these weights. But I fully agree, especially for policy, it would be even more important to know still which variables and why are these weights the way they are now, because they depend, of course, on the data you feed in. So they depend on the variables you feed in. But yeah, thanks a lot.
Great, thank you, Karin. Then, as everybody, you're going to get your AI-generated questions. Who is going to read it, please?
So, how robust are the data portfolio weights across alternative machine learning specification and hyperparameter choices? And could policymakers mistakenly infer similarities to the 70s or to the GFC due to model artifacts rather than genuine underlying structure?
Yeah, good questions, as always. Yeah. I mean, regarding robustness, we didn't check in great details, but it's a good point, because as soon as you change something in the model, is it the hyperparameters, it can also be the variables, also the weights will change. It's like changing, even in a linear model, now if you take out the variables, also the other coefficients may change, and this also holds for the weights. Now, if I take out some variables or I take different hyperparameters, then the weights will change. But it's a good point. We should maybe check a bit more systematically how robust it is. But I think it also depends on how well the model is actually doing and how well it is optimizing or designed. And the second question regarding mistakenly thinking that this is similar to what we saw in the past, I mean, that's a good point. I would say, I mean, we're looking at the model now, and we're looking at what the model gives us. If it's really similar, it's, you know, from the eyes of the model, it may look similar because the data that you feed in is similar to what you observe there. If it really is or not, I mean, I think we still need economists to judge that as well, no? But I think it's at least a tool to, yeah, as I try to highlight, to complement our view. Because even when we look at variable importance, you could ask the same question. No? I mean, the model can give you, okay, wages is important, but is it really? I mean, we still need to put some judgment in when we look at Shapley values. No? So that I would answer to that. Thanks.
Good, great. Malte?
Thank you very much for the great presentation. I like the paper every time I see it. It came to my mind, have you ever looked into what forecast combination is doing in this setting? Because sometimes you even have, I mean, sometimes you have models that you can interpret, but then when you combine forecast, you have the nice feature that usually accuracy improves, but you can't interpret anything anymore. But I think with your approach, I guess you could. No, I would guess that the weights would be distributed more evenly across observations, and that might in some way robustify the forecast. No, might that be the right intuition?
Thank you. Michele, we gather two questions and then you.
Thanks. So I think it was a very nice presentation. I think this is a very useful method indeed, and I think it's very useful for policy. But I have a comment on this thing of the weights of 2022 and compared to the 70s. So in the end, this nearest neighbor interpretation will depend on the value of the predictors, no? Because what you're looking at is these weights are depending on the predictor. So if you have a similar constellation as in the 70s, you will have high weights on the 70s. And in the end, in the 2022, there was a similar level of inflation, but for example, inflation expectations were very different. So we didn't have a disanchoring or long-term inflation expectations. So the result that you do not find sparse weights on the 70s makes sense to me. And in light of that, I would have a curiosity. So maybe this could be done by simulation. So what does it happen when you have a scenario in which basically it's a kind of a mix of the level of the 70s, but the persistence of the 90s. So what are the weights that you're giving to that? And so how does the model learn, you know, how to mix across these two periods?
Okay, we got a third question behind you.
Yeah, thanks.
So it's close.
Yeah, I wondered whether you can do some sort of taxonomy of episodes. You know, once you have a T times T matrix of distances or similarities, you could do some sort of cluster analysis or so to find different types. I mean, I guess if you do clusters, you find just booms and recessions, which is not so exciting. But maybe there's more to it, you know. Yeah.
Okay, yeah, thanks a lot for these great comments. Yeah, forecast combination, I think it's a very nice idea. And yeah, now I'm kind of surprised myself that this comes up the first time that I presented it at least. And I think it's a good point because you could extract the weights from all the models that you want to use, no? And then you could combine them. I mean, the thing is that you would kind of estimate weights again, no? That's what we usually do for forecast combination. I mean, you can also take the average, but if you can estimate the weight, so you would have to apply the weights to the weights as well. And I mean, I think you can still use it for interpretation, but it gets more kind of a mixture of weighting schemes then. But in general, I agree, no? I mean, sometimes we see that it works quite well combining forecasts, and maybe that's also one of the point, no, that different models find different similarities. For example, if you combine them, maybe you get even a better prediction. But good point. I think we should or could look into this, definitely. Then regarding Michele's point, yeah, that's a very good point. So we haven't really checked what would happen if we combine these two kind of scenarios maybe, or yeah, what you mentioned. And definitely, I mean, we got this comment, we got sometimes that maybe it would actually be good to have simulations to really see are the weights the thing that we're expecting to extract. So we started on simulations, but I cannot really give you a clear answer on that because this is not something that we considered, but it's a good point, and I think we should take it on board because it is not that clear. I agree. I mean, what would be an advantage is if we had something that I mentioned before, kind of implied weights, because then you could see which predictors are important and when are the weights high, no? Because then you could maybe get a bit of a clearer picture. Okay, maybe inflation expectations are different, but the model is not even considering inflation expectations as important, then of course it doesn't really find the similarities either. So, but that would, I think, bring more light even into these questions. Thanks a lot. And then the last question, yeah, I mean this method or these weights that I showed you, I mean they are actually also related to this concept. Now there is this literature on clustering, there is this literature on leverage, on influence functions, and so on. So it's related, but it's really a bit of a different thing because we're just extracting them from the model itself. So we're not changing the estimation or anything. It's the same model that you would do anyways and then extract it. But I take your point that it would be nice to look at kind of clusters, within the weights maybe. I mean, that's what we did a bit in this chart that you showed that I didn't show in the presentation when we clustered kind of episodes, to see how important kind of certain episodes are and so on. But no, I think it's a good point and we can look into this. Thanks.
Great. Well, I think we cannot ask more questions because we are at the end. Thanks, Karin. Thanks, Galina. Let's make a round of applause for this great paper.